Today we're going to take a look at section 1.6, which is models in finance. And to start with, we're going to take a look at a few equations. You're probably familiar with them, but in case you have not seen them in a while, the first two are actually simple interest. The first one is I equals PRT. This is the amount of dollars after T years. I'll define what all these letters represent in a moment. The second one is A equals P parenthesis 1 plus RT, dollars after T years. And then compound interest, there's two formulas here. One of them is A equals P 1 plus R over N to the NT, dollars after T years. The second one is A equals P E raised to the RT. It also should say that same phrase down here, dollars after T years. That's actually missing. I'm sorry about that. And then we have the definition of doubling time. Doubling time is the amount of time it takes for an investment to double in value. So P stands for principal, which is your initial amount. So this can either be an initial amount that you put into something, so think about like a savings account, or the initial amount that you borrow from something, so think about like a loan, like a car loan, student loan. R is your interest rate, and it needs to be as a decimal. I'm just going to write DEC. It has to be a decimal. So if they give you 1.5%, a percent is not a decimal, you'd have to turn that into decimal form. T is time, but it's always time in years. So occasionally you'll see things that'll talk about like 18 months. Okay, but you have to turn that into years to use that value, and then you'd have 1.5 years. N is the number of compoundings per year. So if something says annually means one time a year. Semi-annually means 2 times a year, right? Think semi-annual sales, department stores, things like that. Monthly means 12 times a year. Quarterly would be 4 times a year. You could see daily, not in real life, but in a math problem in a book, you could see daily. We're going to go 365 days a year. We're going to ignore the leap year possibility, okay? So that's what N is, how many times in a year it compounds. A is the final amount. After whatever time frame you're looking at. So maybe it's the amount that you have in 5 years. Or maybe it's the amount you'll end up paying in 5 years as you pay off that car loan. And then that I from the very first equation is actually your amount of interest. I do hope that by now you realize that when you borrow money, you don't pay back the money you owe, you pay it back with interest, right? That additional amount that you pay for the luxury of being able to borrow that money is what we're talking about, the amount of money. And the last thing here that you see in these equations is E. E is actually a number, and it's in your calculator. It's approximately 2.718. I don't want you typing in 2.718, but the actual value is in the calculator. One little caveat, because I haven't actually written it here. This one right here, right next to it, that this is continuously compounded. In a business sense, we don't have continually compounded interest. Your book uses it in a couple of places, so I want you to be able to do the problems associated with it. But real life kind of stuff, that's That's not the way that it works. There are things that continuously compound, just not money. All right. Okay, you guys ready to do some examples? Enough writing, some examples. All right, so here's our first example. The question asks, how long would it take? Okay, where's my slide? There it is. Maybe they're out of order. Is that the right one? Mm-hmm. Yep. I don't know what's there. We'll see what that one is later. How long would it take an investment to double if the interest rate were 5.25%? And then we have two possibilities. The first one is, what if it were compounded monthly? And the second one is, what if it were compounded daily? So anytime you're dealing with with a question that's talking about compounding interest, and if it doesn't use the word continuously, you're looking at this equation right here. A equals P times 1 plus R over N to the NT. That's the equation that I'm going to be working with. So over here, I'm just going to jot it down. I think I have space at the top. And we'll fill in the details we know. All right, so it says we want the investment to double. What it doesn't say is how much the investment is now or how much it will be in the future, correct? The reality is that both of those things don't matter. You can choose values and they'll work just fine. So whatever you'd like P to be, the amount it is worth now, you just double it for A. So the easiest numbers to do are 1 and 2. If it's 1 now, it's 2 later. If that feels funny, because these are dollar amounts, that's okay. You can make it 10,000 and 20,000. 5,000 and 10,000, whatever you want. And then this is 1 plus R over N. So R is the interest rate. So the interest rate here is 5.25%. So what would that be as a decimal if we changed it?
0.0525.
That's right, 0.0525. So that's my interest rate. N is the number of compoundings. This one says compounded monthly. So how many times is that? 12. On the outside of this equation is 12, again for the N, and T for time, because that's what we in fact don't know. We're trying to figure out how long it takes in years to do that. So T is unknown. So if you take a look at this, everything's filled in except for T, right? So even with algebra, like from college algebra, we should be able to solve this. There's only one thing that I don't know. I should be able to shift some things around, move it around, and all that stuff. I mean, like, that's fine. But we're actually not interested in solving this with algebra, right? Your graphing calculator is a very powerful tool, and for this class, it's what we're going to be relying heavily upon. Because in reality, if you needed to do something in real life, you'd had access to technology, wouldn't you? You're not going to do a whole lot of number crunching in real life. I mean, like, please know that, 4 times 3 is 12, but, we're not going to actually do a lot of this in real life the same way we would in an algebra course. So here's what you're going to do. I don't care which one goes where, so I'm just going to go in order from left to right. We're going to put 2 in as y1, and we're going to put all this in as y2. There's one thing I want you to be careful of. That exponent 12t, you probably need to put it in parentheses unless your calculator sort of already does so. Because what you don't want your calculator to think is that you're raising it to the power of 12 and then multiplying everything by t. Okay? So my calculator, when I put this in, I'm going to have to put a, I did it again, a caret, and I'll put my 12x in parentheses when I get to that part of it. Okay? So in the graphing part of your calculator, y1 is 2. y2 is, you can write the 1 or you could leave it off, but then you're going to have a parenthesis 1 plus 0.0525 divided by 12, and we're going to raise it to the power of 12t, or 12x in your calculator. For this particular lesson, 1.6, you're welcome to turn your plot 1 off, because we're not graphing anything with the scatter plot, so if you want to go back, pop back up to the very top and just select plot 1 and turn it off, you can do that. Okay, so let's think about this realistically. T, or x, it doesn't need to be negative, right? It's not going to double in the past. So as you're setting your window, you can start your window as the x max or x min is 0. It's not going to go backwards. There's not a real good indication of what we should make the x max, but usually 20 or 30 will do it for a doubling problem. So Choose one of those. I don't care which one. And then you're going to hit zoom 0. That's zoom fit. So what zoom fit does is it takes the X max and min that you put in and it adjusts the Y max and min to be a good picture. So that you don't have to try and pick what you want your max and min for Y to be. So right now, my X min is 0 and my X max, mine is 20. And when I do that, the graph that I get looks something like this. Hang on. Shell screen look like that? Yeah? Good.
I get lost.
Okay, where are you at this point?
All right, what did you put in for Y2? You put in 1 parentheses.
I put it in just like this. That's what I put in.
You put it in as 1 plus.
Yeah, I put a parenthesis, 1 plus 0.0525
You didn't
over.
have to put an extra parentheses around the interest divided by 12?
Nope, because your calculator understands order of operations. It will know to divide before it does the addition. And then I put a caret and I put 12x, and that part needs to be in parentheses. Because again, it knows order of operations. We need to make sure it understands to multiply the 12 and the x. Okay, does anybody's screen when you graphed it not look like the one that I sort of sketched? Okay, that's good.
Did you say the graph?
Max 20 and then zoom 0 for zoom fit.
Excellent. I'm sorry.
It's right here, Sarah, on the screen. My screen went off. You guys should have told me my screen went off. Okay, so I have an X min 0, X max 20, zoom fit, and I have a graph that looks something like this. This horizontal line is the Y1 that we put in. Was it on briefly? It was not?
You just had your code.
We're just going to try again, right? We're back up. We're going to try again. So that horizontal line is Y1. It's the value you entered on the left-hand side, which was my 2. And this curve is Y2, which was the equation with the power x in it. Okay. Yours does not look like that, Martin? Okay. Okay, anybody else's not looked right? And then back off, look. Okay, one more time. This is the answer to my question right there, that big old red dot. I just need to figure out where it is in the calculator. So we've done this at least twice together in class. The way we find that location is that we hit second, we hit the trace button, which is the calculate menu, and we select option number 5 that says intersect. Because it's only crossing once, when it says first curve, we press enter, second curve, we press enter, guess, we press enter, and it will give us a value. At the bottom, mine says x equals 13.23, and I'll round to 3 decimal places, 2. It says y equals 2, but we know y equals 2. That's what we were trying to get it to equal, right? It's the x value I was looking for. So the question asks, how long would it take an investment to double if the interest rate was 5.25%? And the answer is 13.232 years. That's how long it take. Okay. We're going to compare that to what happens if it's compounded daily. I'm going to have to move some things around on my screen to do that. But any questions on part A? Okay, your part B actually, you can use a lot of part A as is. In particular, it's still a 2, right? We're still doubling things. We still have 1 plus 0.0525. The difference is that it's compounded daily. And daily means how many times in a year? Yeah, 365. So as you're entering this in the calculator, mine will have a caret, but it will be 365t. So you're just changing the 12s in your calculator, where the equation is, to be 365. So you're still putting this in y1. You're still putting this in y2. We're going to go through the same steps where we're looking for the intersection. So your graph should still be a good window for it. You shouldn't need to manipulate that. So second trace, number 5, hit enter 3 times. And if I do that on this one, it tells me my x value at the bottom is 13.204. And it's years, so I'll just write it all at one time this time. It takes us slightly less, ever so slightly less, but a tiny bit less time to double if I have daily compounding as opposed to monthly compounding. Does that make sense? Any questions on that? Okay. Couple of vocabs. Nominal rate and effective rate. You've probably heard of APR and APY, even if you don't know what they are, because it's one of those things that are commercialized. You see it on commercials all the time about financing. You've got 0% APR financing for up to 60 months, right? Or they'll say the APY, or the annual percentage yield. The APY is 0.9%. So here's the difference between these two. APR, the nominal rate, is the annual percentage rate that we keep using in all the equations above. Okay, that's the R. APY, or the effective rate, takes into consideration interest compounding upon interest. So it's called the annual percentage yield. The APY is always a slightly larger number than the APR. And it's found by using this equation. Now, you'll notice that this piece looks a lot like the compound interest piece without the T, right? Like what we just put in the calculator. It looks a lot like that. And there's not a slide showing this, but let me actually do the APY for continuously compounded interest as well. If you were doing this for continuously compounded, it's e to the r minus 1 times 100. And just put yourselves a note that that's continuous interest. Okay, so if you have a credit card, you've probably been told, maybe you don't remember, what the APR on your credit card is. It would come in the bill every single month. It'll tell you what your APR is. A 19.99% would not be unheard of for a credit card. Credit card percentage rates are usually very, very high. Okay? That 19.99% compounded monthly actually is the nominal rate. Okay, so that is what we're actually being given when we're being told that on such a statement. It's not the APY though, okay? So this is the R, right, in all these equations we've been working on. Because it says compounded monthly, the APY formula that we're going to use is this one. The only time we'd use that other one that I wrote in there is if it said compounded continuously. There's an example in your homework. That's why I mention it. But the one that we're doing right now is the compounded monthly one, the one I just drew the arrow to. So we're over here going to write down that formula. The APY equals 1 plus R over N raised to the N minus 1 times 100. We just need to use the R and the N that we have. So what is the actual R value if my interest rate is 19.99%?
0.199.
Right, 0.199. Move the decimal point to the left. So over here, I now have 1 plus 0.1999 over. What is N? 12. It's compounded monthly, so it's 12. I raise this to the power 12, subtract 1, multiply by 100. Okay, so parentheses are sort of this necessary evil that exists. And they sometimes can be really tricky to make sure you start them and you close them properly in your calculator. Inside of a graph, right, you may not have a choice to do that depending on your operating system. But here, you actually have lots of choices. So if I were doing this problem in the calculator, what I would suggest you do is simply work from the inside out. I'd have you take your calculator and actually put it right inside of it, the regular screen. 1 plus 0.1999 divided by 12 and press enter. Okay? I don't want you to use that and approximate it, but your calculator should be telling you something like 1.016658333. Okay? So we've done the part that I've sort of underlined in red. We're going to raise it to the 12th power. So use that little caret on your calculator screen and put to the power 12, and then press enter again. Okay, so you're using the previous work, all that 1.016658333. Just like it is, just press caret 12. Your calculator should now say 1.219271115. Does it say that? Okay, so again, we've done everything I've sort of highlighted and marked now in red. Our next step is to subtract 1. So again, from your screen, just hit -1 and press enter. Now it should say 0.219271150. Okay, last step, you're multiplying by 100. So what you're really doing is just order of operations on the problem, working from the inside out. And you're doing it in part to make sure that there's not a parenthesis problem as you work through. Could you enter it all with the parentheses and be really careful? Sure. If you want to do it that way, that's fine. You can. I just find it easier to just do the steps inside out. You're going to do the same amount of work either way. And what you end up getting is 21.9271150, something like that, right? Your calculator says that. So we will say that this is 21.927%. if we have, well, I'm going to say if we haven't made any mistakes, but we should be getting a number bigger than the 19.99%. If we were to have gotten a smaller number than 19.99, it means we made a mistake. Because just because we got a number bigger doesn't mean we did it right. But at least we stand a better chance than if we had gotten a number smaller, because then we would know we got it wrong. Okay? All right, one more question in this section. Let's take a look. An investment question. How much money would you need to invest today at 10% APR, compounded monthly, to have enough to pay for a down payment of $40,000 on a house in 7 years? What would you have to put in the bank today? So this is sort of the imagination that somebody died and left you a bunch of money, and you're going to spend a bunch of it, but part of it you're just going to stick away. And you feel like maybe 7 years from now is a good time that you would probably be ready to, put down roots somewhere and buy a house, because you don't want to buy one too soon, because you might get, moved around when you're first in your job, something of this nature, okay? So you've been given a bunch of money and you're trying to figure out how much to save of it right now. So this isn't sort of a monthly saving process, it's a total savings at the beginning. All right, so we're going to use that same equation that we had back at the very beginning, which was A equals P times 1 plus R over N to the NT. So far what we did was doubling time, right? How long it took for a specific investment to double. But what we know in this case is that eventually we want to have $40,000. Right? That's the outcome we want. What we don't know is the P. What are we needing to put in now to make that happen? 1 plus. R is my interest rate, which is 10% here. So what is 10% as a decimal? 0.1. Divided by what? 12, because it's compounded monthly. It's raised to the 12, but this time I know the years. It is 7. Okay, everybody good? Okay, so my first suggestion in terms of solving this is to just figure out what 12 times 7 is, again, so that we don't have to worry about the parenthesis issues. So what is 12 times 7? 84. Wonderful. So if you were to put this in your calculator, then I would just put all of this in your calculator, regular screen, or you can put this in, press enter, and then raise it to the power 84. Did you get about 2? 2.00 and then some more stuff after. Awesome. We're actually going to write that down here on this one because of our keystrokes in our calculator being a little more complicated if we don't. 2.007920.153. I'm just going to write them all out so that I don't lose anything in rounding by accident. How then would I solve for P? Yeah, I would divide 40,000 by that number. That's exactly right. So I'm going to divide by the 2.007920.153. So these are going to cancel. I'm going to be left with P equals, I'll shift it so I have some more space. So what is 40,000 divided by that 2.00 number? And it's dollar amount, so we need 2 decimal places. 11 cents. Awesome. So we would need to save almost $20,000 today. And we'd have enough if we had 10% interest rate. We'd have enough in 7 years to have that down payment of $40,000. Are you good with that? I mean, like, that would be amazing, actually. It's a little difficult to find generally 10% interest rates, at least at banks. We'll talk more about saving later. All right, any questions from 1.6? All right.